In this video, we're going to finish off section 5.1 by doing definition 5.1.4, example 5.1.4, and looking at a geometric rationale for Fubini's theorem. So definition 5.1.4, the average value of a function f of xy over a region R is defined as f average is 1 over a of R, where a of R is the area of the region, times the double integral over that region of f of xy dA. So two things to point out. One, firstly, this region doesn't have to be a rectangle. So in the next section, we're going to see how to do a double integral over a non-rectangular region. But this definition is true for any kind of region. And the second thing is to compare to Cal 2, where f average was 1 over b minus a, the integral from a to b of f of x dx. When you had a single variable, this was the length of the interval. Now we have got two variables, and so we're up one dimension. We've got an interval in 2 dimensions, which is a rectangle or a region. So the area of the region corresponds to the length of the rectangle, the length of the interval. So example 5.1.4 is asking us just to apply this formula. And conveniently, it's a function whose double integral that we have already found in a previous example. So using here f average is 1 over the area of R times the double integral over R of e to the x, or e to x times y, e to the x squared plus y squared times dA. Now the area, well, that's the area of a rectangle. So we have got a rectangle which goes from 0 to the square root of ln 2 in the x, and from 0 to the square root of ln 3 in the y. And so base times height, we've got the root of ln 2 times the root of ln 3 is the area. And we had found that this double integral in a previous example came out to be, using Fubini's theorem, 1/2. And so our average value is 1 over 2 times the root of ln 2 times ln 3. And now to close off the section, why did Fubini's theorem make sense? A geometric rationale for this, and that is by looking at volumes by cross-section. We're going to work with the interpretation that the integral, the double integral, is the volume under a surface. And so if we go and draw ourselves a surface over some rectangular region, so let's draw our region underneath, and we're looking at interpreting the volume under this graph as the double integral. So this graph here, we're going to need twice. I'll copy this and make a second image of it over here. And now the first way that we're looking with Fubini's theorem is taking cross-section in, well, if I do in this variable here, we're imagining taking a little cross-section and filling out the area of that cross-section like it was the area under a curve. And that area under a curve, we know, well, let's shade that in a little bit too. The area under a curve can be calculated with a single integral. And so if we fix that value for the moment at whatever x value that lends out by being, then what is happening is that y is varying. And so this integral we can think of as the integral from c to d, if those are the bounds here, if this is c back here and d here, and that would make this a and b, that's an a. a and b in the x direction. That would be for the integral from c to d of our function f of x, y, dy. That's the area under that curve. Well, that's only a single area. We want the entire volume, so we want to add these up in the x direction. We want to go entirely in the x direction and sum up all of those areas, infinitesimally small, which means that we want to integrate in the x direction from a to b dx. And so there is the expression of the iterated integral that represents the volume if taking cross sections in this direction first and then summing them up in the other direction. But if these things are continuous, there's no reason that my cross sections have to be in that direction first. I could take cross sections in the other direction. Why not? So if we start out by taking cross sections like this and imagining that we have a curve here with area underneath again. So then we're looking at this area where x is varying and y is fixed at some y value. And so x is going to go from a to b. This integral here, the area under that curve would be the integral from a to b of the function, where y is fixed, dx. But of course, to get the volume, you want to have the cross sections all added up in the y direction. So you would also integrate from c to d, where this is c and d again in the y direction. You'd add up all those cross sections, infinitesimally small, so you'd be integrating in the y direction, and you would get, again, the volume. And if this is the same surface and the same volume and everything is continuous, Fubini's theorem says that these things are equal. And so there's the geometric rationale of thinking why iterated integral works and why it works in either direction to give you the double integral over a rectangle of a function f of xy dA.